Welcome to this video. In this session, you will be learning the speed control of universal motor using AC voltage controller. So this is the power circuit. So the supply voltage is 230 volts 50 hertz and there are two thyristors connected in anti-parallel and we have a universal motor connected in the loop. So we are not using the 1:1 transformer here. The 230 volts we are going to feed directly to your AC voltage controller. This circuit is going to convert from fixed AC to variable AC voltage. Frequency remains same in the circuit. First let us go to the control circuit. The control circuit comprises the rectifier circuit, ZCD, ramp generator, comparator, high frequency pulse generator, and we can expect the pulses at the G1, K1, G2, K2 with electrical isolation. To this module EC08B, we are going to give both AC voltage as well as the DC voltage. So AC voltage is 15 volt AC 50 hertz and DC voltage we are going to give 0, 15, minus 15 constant values for the op amp from the regulated power supply. Now let us see the connections. This is a step down transformer which is going to step down from 230 volts, the Bescom point, to 15 volt AC. It has got 15, 0, 15. We will be using only 15 and 0 connected to your control module named EC08B. The 15 volt is fed here, which is AC, and at the same time we are going to give the 0, 15, minus 15 from the regulated power supply. The red color knob is 15, green is 0 and black is minus 15. Is a constant voltage that is fed to your control circuit. You can observe this. Same, the 15, this is 15 and this is 0, this is minus 15. So this voltage is for the operational amplifiers. So to start with, the 15 volt is fed here. Let us measure the 15 volt AC in the CRO. If you look at the CRO here, since the voltage is exceeding the values, set the voltage knob here. This is our y-axis, this is the time knob, and let us see what's the amplitude we are getting here. So when you look at the amplitude, we are getting around 1.1 unit peak value or the amplitude. So 1.1 peak value of the amplitude into 20. So 20 into 1.1 is 21 volt. So this is a peak value. We have given the 15 volt AC. 15 is the RMS value. So in the CRO we can see only the peak value, not the RMS value. So 15 into root 2, we are going to get around 21 volts peak. Now let us see the frequency of this signal. So set the 0 starting point of the voltage from the reference. Then you observe there are 4 units. 2 units in the positive half cycle, another 2 in the negative half cycle. Totally 4 units are there. So 4 units into time knob is 5 millisecond. So it is 20 milliseconds. Inversion of 20 millisecond is nothing but 50 hertz. So this supply is 21 volt peak value RMS 15 and the supply frequency is 50 hertz because we are getting time period is 4 units into 5 millisecond, nothing but 20 millisecond. 20 millisecond. 20 millisecond inversion is 50 hertz. Now let us see the voltage waveforms at different points. Now let me connect the CRO probe negative and 15 volt we are expecting to see there. So let me show you. It is showing around 1.3 into 10. Roughly 1.3 or 1.4 nearly. 1.4 into 10 is 14 volts we are getting DC. 14 volt you are getting DC and minus VDC again 1.4 into 10 is minus 14 volt. That's the DC voltage fed to the control circuit. Then you go to the output of the rectifier. Output of the rectifier, we come to the output of the rectifier. This is the rectified voltage. Here we can expect same 21 volts. You can observe that's a 1, 2, nearly 2.2 units are there. 2.2 into 10. So it's roughly 2.10 is 22 volts or nearly 21 volts. Similar to the supply voltage, 21 volt peak, whatever you have fed there. Now it's a rectified voltage. The rectified voltage is fed to the ZCD. zero crossing detector. What ZCD will do is at every zero crossing is going to give a small pulse. You can observe. Let me set it here. Zero reference. This is a 0 degree, 90, 180, 270, 360. 0 degree I have a 1 pulse. Then 180 degree of 1 pulse. 360 of 1 pulse. Which means that every zero crossing the sine wave, you are going to get 1 pulse there. The amplitude of that is 0.8. 0.8 into 10 is 8 volts. So the knob is in 10 volts. So 8 volts is the amplitude of this pulse. Then ramp generator. So at every zero crossing, you expect a negative ramp. The ramp starts from the highest value, that is 8 volt. It's going towards 0. It's a negative slope. So it's a negative ramp. So the amplitude of this is almost 0.7 into 10. Around 7 volts you are getting the peak value of this particular ramp signal. Then we have a variable DC voltage. You can see soft start capacitor. The knob. When you vary this knob at point E, you can expect a variable DC voltage. So you can observe in the CRO, I am varying the voltage. It's varying. Let me put it in the 5 volts. You can see it's varying from 0 to 5 volts. That is 0 to 1 unit. I kept the voltage knob in the 5 volt. So 1 unit into 5 volt is nothing but 5 volt. This is a variable DC voltage. This voltage we are going to compare with the ramp voltage to generate the pulses. Now let us see output of the comparator. So here we expect both the negative area and positive area of the waveform. So I am varying the DC voltage. DC voltage is compared with the ramp signal. So we are getting the variable pulse. The pulse is varied. The time is remaining same. Only the on time is varying here, or we can say firing angle alpha is varying otherwise. Now how to measure the firing angle alpha here? Let us see. We kept the voltage knob in 5 milliseconds. Every unit is 5 millisecond. We know that 20 millisecond corresponds to 360 degrees. 5 millisecond corresponds to 90 degrees. So every unit is always 90 degrees here. The moment you set your time knob to 5 millisecond. So every unit is always 90 degree. So there are 5 subdivisions are there. 90 by 5 is 18 degrees. So every subdivision is 18 degrees. Now if you observe, time being is showing the minimum alpha. Now I kept it at one subdivision. So my pulse is starting from one subdivision, nothing but 18 degrees I have set it here. Then you go to second subdivision. Second subdivision from the reference. So it is 18 2s are 36 degrees. Third subdivision, 18 3s are 54. 18 4s are 72. 18 5s are 90. 18 6s are 108. 18 7s are 126. 18 8s are 144. So we can vary up to that. So this is almost alpha 0 and alpha is tending towards 180 here. So this is how we can vary the firing angle here. So the same pulses when it fed to your SCR, we can expect the firing angle in similar fashion. Then let us see the isolated pulses at G1 K1 and G2 K2. These pulses are high frequency pulses. It is chopped to very high frequency as well as it is isolated, so that if any problem occurs to your power circuit, it won't carry to the control circuit because it's electrically isolated. Now we have a G1 K1 pulses which is connected, CRO is connected there. You can see G1 K1 pulse is high frequency. Let me vary the time frequency. You can see high frequency pulses you can expect here. Let me set always 5 millisecond to ensure that my every unit corresponds to 90 degrees. Corresponds to 90 degrees. Now we set the end point of the pulses at 180. When you vary the DC voltage, we can expect even the firing pulses are varying here. So this is alpha 0, alpha 90, alpha towards 180. So 180 practically we cannot achieve, even alpha 0 we cannot achieve. It starts from around 8 or 10 degrees, it goes up to 170 degrees. So these are the pulses we expect at the G1 K1 high frequency pulses. Similarly, let me change it to G2 K2. G2 K2. G2 K2. So we expect the same pulses, but this is out of phase. These pulses are out of phase compared to G1 K1 because SCR1 will conduct during positive off cycle, SCR2 will be conducting during negative off cycle. So when you come to the power circuit, power circuit. So during positive off cycle, SCR T1 will be forward in the forward blocking mode or a forward biased. The moment you give the pulses to G1 K1, then SCR moves from forward blocking mode to forward conduction mode. Current flows from the phase to T1 motor back to the neutral. During negative off cycle, SCR2 will be in the forward blocking mode or a forward biased mode. The moment you give the pulses to G2 K2, SCR2 moves from forward blocking mode to forward conducting mode. Current flows from neutral motor back to T2. Now let us connect the power circuit and then see the final values. Let us see the connections for the power circuit. We know that there are two SCRs connected in anti-parallel. So this anti-parallel connection will be in series with your power loop, in the power loop. So the two SCRs are connected in anti-parallel such a way that cathode of the first SCR is connected to the anode of the second SCR. Similarly, anode of the first SCR is connected to the cathode of the second SCR. So they are connected in anti-parallel. Now 230 volts wire is which is taken from the Bescom point, 230 volts from the panel. This is the red color wire is the phase wire. Phase wire is connected to the one of the anode of the SCR. Cathode of the same SCR goes to the your motor connection, and another wire is nothing but the neutral wire that is going to the your Bescom point. So simple loop, power loop, where phase is fed to the anode of the first SCR, cathode to the motor, and another point of the motor to the neutral wire. So we connect the multimeter in the AC mode. Connect the multimeter in the AC mode. Now we go to the CRO to measure the firing angle. So always ensure that the falling edge you keep it at the second unit end point. So we know that since we have said the time period is 5 milliseconds, every unit corresponds to 90 degrees. 90 degrees, and subdivision corresponds to 18 degrees. So we have turned on the supply. As of now, the firing angle alpha in the CRO is, it is a from the zero reference, 1 unit is 5 subdivisions, 6, 7, 8 subdivisions are there. So 8 subdivisions corresponds to 18 8s. 144 degrees is the firing angle as of now. Now let me increase the firing angle and ensure that the minimum speed is obtained. So this is the minimum speed is showing around 560 rpm. This is the minimum speed kept there, and firing angle here is it is 7 divisions are there. You can observe from the zero reference here. So 5 divisions, 6, 7 divisions, 18 sevens are 126 degrees firing angle. Speed is 500, and AC voltage is 17.72 volts nearly. Then let us set this firing angle 6.5 into 18 degrees. So this is the 6.5 degrees. You vary in steps of the 99 degrees. So this is 6.5 into 18 degrees. From the zero reference, it is 5 subdivisions, then 1.5 subdivision, 6.5 subdivisions into 18 degrees. The speed is increased to 1673, and voltage is 82.7 volts. Then let me keep the firing angle at 6 precisely. 6 subdivisions, 6 into 18. The speed has increased to 3137 or 3143. There will be small fluctuation will be there. You take the reading immediately. Respective AC voltage is 92.8. So let us keep the firing angle 5.5. 5.5 into 18. The speed has increased to 4312, and voltage is 101. And go to the 5 subdivisions. The speed should not exceed more than 5000. So it is increasing nearly 5000. So this is one of the readings you have to take very faster. It's around 5369. Voltage, RMS voltage is 111. Then reduce the firing angle. So this is the way of conducting the experiments. You vary the firing angle in steps of the half subdivision. Every half subdivision corresponds to 9 degrees. At the rate of 9 degrees, you can take the various readings.